microscopically.
Yeah.
So you do a per addition mode and a per subtraction mode, 2 particles and 2 holes, and you have SD there, and you have 5 or 6 or of that size of your subspace or what. No, I'm asking you, how many S bosons? Take it the nucleus you like. How many S bosons and how many D bosons you have?
Well, that's very simple.
But tell a nucleus that you like.
You just take the chosen valence space, divide it by 2, and so you can have 1 boson up to 10 bosons.
Up to 10?
Yeah.
Yeah. So now you tell to me that this description based on what I would call per addition and per subtraction modes, monopole and quadrupole, namely 2 particles or 2 holes, can describe all the varieties of observables, be 2 values M1, single particle occupation numbers, 2 particle transfer absolute core sections. How many effective charges or matrix element do you put? Because if you have to reproduce the B2 in that subspace, you have to put effective charges.
Effective charges. So
Yeah, how many do you have? How many parameters, how many effective charges do you have?
Just 1.
Just 1.
Yes.
And for the absolute cross section of the 2 particle transfer? You don't know. And if, the spectroscopic factor is just 1, or you for the different single particle states? How many?
Just 1.
Just 1?
Yes.
And with that you explain all the single particle states. It's not that I doubt of what you tell to me. I just say it cannot be, simply. It can't.
Microphone, please.
I sort of come from the same place you come. You compare, you have nice comparisons what the advantage of QRPA, Shelm, etc. Now, it is said that the IBM deals only with the valence nucleus. So you have excitation, that's what the IBM, we were told, does, that it does it only within the limited space of valence nucleus. But in the QRPA or in the RPA, you go outside of that space.
Yes,
you go. So how come that these two things come together and mesh? Is the effective interaction somehow, effective charges, or
we do not know that yet. What is the reason that the results are so
you don't know?
No, we don't know.
No, I can tell you. You just parameterize
But it does.
You just put parameters in order to reproduce the data, and then you come close.
Then they reproduce, you mean?
Of course.
If you
There's
fit
no
them.
way out.
Okay.
Let me just compare a bit shell model calculations, quasi-particle random phase, and IBM. You see, the shell model has the advantage that you take all the configurations in a very restricted single particle space. Typically, for germanium-76, one can take 5 levels. While in quasi-particle random phase, one can take up to 23 levels for germanium-76, a very large single particle space, but only restricted configurations. That's also, even in IBM, you even more restricted configurations, which you can take into account. Now, if one compares now quasi-particle random phase with the shell model has a tendency to be smaller than the quasi-particle random phase. If we take the small space from shell model, we get similar values than the shell model. You see, that's so we say the shell model get the small results due to the fact that they have such a small single particle space. Yeah. In the IBM, you have a very strong restriction of the configurations, even more than in the quasi-particle random phase, what you take for the configurations. That also reduces. And by that, I would expect that IBM in the shell model gets very similar results, but different results than the quasi-particle random phase approximation. Since I did not do any IBM calculations, I cannot say if that is true. It's only a hinge. You see that there are different deficiencies in the shell model, and a other deficiency in the IBM, naturally also a deficiency in QRPA. But the deficiency in IBM is even stronger than in QRPA, and that restriction makes it then so small that in the shell model results, which have this very small single particle space, 5 levels. Result of the whole calculation for germanium 76, 5 levels, while QRPA has 23 levels, 4 to 5 times as bigger space. But okay, one must admit, shell model can take then in that small space all the configurations. That is also a big advantage. But if you increase the single particle space, you know, then the dimension explodes and one cannot calculate it anymore.
So can I have a related question to these here? So it's not clear, I mean, from what Professor Fessler say, it looks like your single particle space is as small as for shell model. Can you be precise? For germanium 76 you use those 4 orbits which you use?
Yeah.
No, okay. So therefore,
Yeah, we can only
it's
take
clearly that
measures.
as far as you have the exact result and you disagree significantly, something is missing. And what is missing is what I show in my talk, and is exactly what is missing in QRPA. For the line neutrino exchange, you have the pair coupled to 0, which is big. It's as big as ours. But you don't have the 2 because it's come from high seniority, which you miss, and QRPA is missing. So you don't have this big cancellation we have. For the heavy neutrino, you have exactly the same result with ours, because there is no such cancellation.
You see, the restriction is not in the IBM, is not in the single particle space. The restriction are the configurations you are taking.
But in addition to that, because she's mapping the bosons in the single
I
particle.
am not criticizing the single particle space. You see, you have quadrupole states and S angular momentum 0 states. That's it. And you build everything by that state.
Yes.
But the single particle space is the same.
Yeah, the single
The single particle space can be big, but you...
Can be, but it's not.
I
Come vuol dire? No, no.
One minute. Because they aren't doing mapping.
I know so they're doing math.
But we have truncation.
You are on the S&T bosons, but you really produce very well nuclear levels of Lorentz state. But quite important is in case of beta decay or double beta decays. Spin ice spin correlation 1 plus and 2 minus and 3 plus spin ice spin mole, that is Pn. And therefore, I think whether your wave function is good or not can be really checked. Not, by comparing single beta decay 1 plus 2 minus strength distributions from 0 to 20 MeV in that region, how your wave functions really reproduce observed such strengths up to 20 MeV. If it's so, maybe it's good, but I'm afraid it's not.
We haven't done that yet, but we are planning to do so.
And also, I think GA is a little bit, to me, a little bit confusing, because if you define GA is due to, not including non-nuclear degree of freedom, then that is fine. But I think in your way, I think you say that GA is defined just the deviation of your calculations and experiment. Is that your GA?
So the
Therefore, that
question is
means,
coming from the limited model space.
yeah, therefore I think your GA may include not only such a non-nuclear degree of freedom, but also maybe I think your matrix element is somewhat different than such deviations also include in GA. So that's it's confusing, I think.
But projected wave function on all the subspaces, as you say, single nuclear beta decay, double beta decay with neutrinos, 1 particle transfer, 2 particle transfer, project on all that, and tell me how the wave functions look like.
Yeah, so
Precisely.
therefore I think TA is very much model dependent, I think.
And if it works out, fine, everybody would do it IBM too.
Just a deviation.
Absolutely.
Absolutely.
No
Okay,
question.
okay, now I'd like to close this
Very
session.
strong.
I thank all of the talkers.